So I'll get started. So I hope you guys have noted, I sent you an announcement, right? About Mission 2, it's up there. Mission 1, of course, has already been posted. If you look at it, you'll see that, both of them are, they should be echoing in some sense the required homework, the recommended homework. I'll begin, like I did the other class, by asking if there are any questions about the video from last time. Is there anything you'd like to see me talk more about? Mm-hmm. So you say, I take your video question and raise you a homework question. I'll allow it.
Yeah. I have a question about I don't have a homework video, but I was wondering about number 7B, and how you set it up, how you do the next part.
Oh, sure. So let me work an example. So here is like problem 6. So factor completely. So I'll look at x to the 4th minus 13x squared plus 12. All right, so I want to factor, that's given, I'm going to factor that completely. All right, so this is a quartic. So it's kind of funny. I think cubics are harder. Like the quartics, which I will typically ask you about, they all pretty much come back to the same trick, which is what? Think of x squared as its own variable, and like try to look at this in x squared. What is this? So like this will give me back the x to the 4th. How do I get 12? I get 12 from 12 and 1. And so I need a minus 13, right? So negative 12 and negative 1, right? Now I think I forget how the 1 in the, well, anyway, let me go on. Okay, so this would be x minus the square root of 12, x plus the square root of 12, right? X minus 1, x plus 1, right? Because we got difference of squares, right? Using the difference of squares identity, right? And that would be that, right? Let me do one more example. I'll call that A. That's like problem 6. Let me do part B because I wanted something else to happen here. So how about x to the 4th plus x squared? Factor completely. This one's even easier, right? We just pull out x squared, and what does that give us? Plus 1, yeah, plus 1. And if we're factor completely over, and some of you guys, I know if it happened in the other class, it's happening here. What does this symbol mean? Real numbers, right? Some other people in the other section were like, I don't know what that symbol means. I'm like, If you have questions like this, you should ask me, right? Please. If you don't understand notation, that is the first thing you should email me about or ask me, okay? I'm here to help you. Do not labor in vain. If you don't know what the words mean, you can't solve the problem, right? So, or the symbols in this case. But yeah, that's the real numbers. So this is factored completely over the reals, right? Now, if the question was to factor over the complexes, I could go on, right? If I was going to factor over the complex numbers, I could further simplify this as since x squared plus 1 is also equal to x squared minus I squared. So we can look at x squared plus 1 as a difference of squares if we use complex numbers. Yep.
But now that you change the directions to over the real numbers, did you have to know that extra step?
Nope.
Okay.
I sure didn't. So this is if directions asked for factoring over complex numbers. But if it doesn't, then we're done right here. This is it. Because we can't we cannot further factor x squared plus 1 over the reals, right? Like what we need to factor that is not available in the real numbers. So that's just kind of it. Okay? Now, your question was number 7, right? But to understand number 7, I need to have number 6 done. So number 7, so this is going to be like problem 7. But for the examples I have here, so like follow-up A, I would have x to the 4th minus 13x squared plus 12, which, by the way, we figured out was x minus square root of 12. I mean, you don't have to write all this in your solution. I'm writing it down right now to try to explain, since there's a question. But I think, honestly, no further writing is really needed for problem 7. It's totally legitimate to just write down the answer on the basis of problem 6. See, because once we've factored completely, we can read solutions from that. Right, x is equal to, yeah, plus or minus the square root of 12, or plus or minus 1, right? Or you could list them plus root 12, minus root 12, 1, minus 1. There's four solutions. Now for part B, if we're just solving, I'm going to say find real solutions, okay? And I forget what I said in the homework. Did I say find all real solutions? Yeah. Okay, good. Actually, it's ambiguous. I didn't tell you which. But let's, for the sake of specificity, say that problem 7, I'm looking for just real solutions, okay? Real solutions. So that comes into play for the second one, right? Because if I have x squared times x plus 1, x squared plus 1, rather, equal to 0, then either x squared is 0 or x squared plus 1 is 0, right? But can x squared plus 1 be 0 for any real x? I mean, it cannot, right? There's no real solution to x squared plus 1 equal to 0, right? In fact, the solutions are plus or minus I. The solutions are imaginary. So if the context of the problem is to find all real solutions, we're only going to find one real solution here, just repeated, right? So this implies x equals to 0 is in fact the only solution. And I usually would say I like to count, I mean, to me that's a double solution, right? But you have 2 zeros there. I don't know. And here we get into pedantics. Is it one solution? Is it 2 solutions? For the purpose of certain discussions, you'd like to say it's 2 solutions later. But anyway, 0 is the only solution there.
I had a question about how do you write inverted notation?
Oh, the interval notation? Great. Yeah, we'll do a lot of that today. I'm going to solve a bunch of inequalities for you guys. And every one of those, we're going to write our answer in interval notation. So that question will answer itself as we go on. But generically speaking, that's like the with the parentheses or the square brackets, or it could go to plus or minus infinity, or like interval notation for the reals itself is minus infinity to infinity. But we're going to keep hammering on that all of today. Just not yet, because the solutions to equations are not intervals, are they? They're just like a finite list of numbers for us here. I mean, I can give you an equation which has the whole real numbers as its solution. You know what it is? How about this? Like x times 0 equals to 0. Find all x that solves that. Yeah, any x works, right? So the solution to that really silly equation is the whole real numbers. But for the kind of equations we usually look at in here, polynomial or algebraic equations, we're going to usually have like a finite list of solutions, typically. Next semester, when you guys look at trigonometry, sine, cosine, things like that, those guys will have like an infinite list of solutions, because sine's got that like periodicity, so you keep getting lots and lots and lots of solutions, but that's for next semester. Other questions? If you'd like to see me, if you'd like to see me solve a problem like one of the ones in the mission one, I'm happy to do that if you have a specific one you're interested in. Like I could solve something like, here, I'll tell you what, I have a suspicion you guys probably need to see it. Have I talked about how to solve equations involving absolute value yet? I'm not sure if I've done it in here. So I'll just give you an example. If I wanted to solve, say, the absolute value of 3x minus 2 plus 7 equals to 10, what would I do? So, like, first of all, isolate the absolute value by itself, right? So, like, this is absolute value of 3x minus 2 equals to 3, right? And then the key thing for absolute value is to notice that, absolute value of a, what is it equal to? Yeah, plus or minus a, right? Depending on whether a is positive or negative, right? So logically speaking, if you want to get rid of the absolute values, you can just put plus or minus 3 on the other side and work with that. That's one way to solve these. The other way is to break it up into two equations and solve them separately. Like you could solve 3x minus 2 equals to 3 is my one equation, 3x minus 2 equals to minus 3 is the other equation. Solve those separately, they'll give you two solutions. We should have two solutions for this absolute value equation, or none at all. But I think we'll have some. How would you get no solutions at all in this kind of problem? What if instead of having 10 here, I'd had like minus 10? Yeah, then I'd have this absolute value equals to like minus 17. And the absolute value has to be non-negative, right? So you can't solve absolute value equal to something negative. But, okay, anyway, so we got 3x equals to 2 plus or minus 3. So x is equal to 2 plus or minus 3 divided by 3, also known as 2/3 plus or minus 1. So I guess you could say 5/3 or minus 1/3 would be the solutions here. And you can go back in and try them, right? Like if you put in 5, you get 5 minus 2, which is 3, and 3 plus 7 is 10. Great. You plug that one in, you get minus the absolute value of minus 3 plus 7, which is again 3 plus 7, which is 10. It's easy to go back and plug those in and check that they work. But this is how I would solve absolute value. Something kind of like part B. Let's see if I can find, rather than making something up where it will go badly for me, just give me a second here. I will scan through the recommended homework. As an example from the textbook, I'll make sure I don't solve the one in your homework by accident. You're like, yeah, that's okay. No need to check on that, right? Ooh, I was about to solve your part D. That wouldn't have been good. Let's see here. I think this one I have not assigned, but it's like the ones I've assigned. Square root of 5 minus x plus 1 equals to x minus 2. How do we solve such a thing? So step number, yeah, move the 1 over, isolate the radical, right? X minus 3. Now we square both sides. Did I do this one? Oh, man. I'm sorry if I already did this. But congratulations on remembering. You're doing better than I am. The thing is, I'm doing this in like 4 different classes. I will get confused about what I've done in here, what I haven't. You'll have to keep me on the tracks here. Is that right? Let's see here. So if I move, add x to both sides, that gives me minus 6 plus 1, which is minus 5. Take 9, subtract 5, I get 4. And then, oh, because I added x to both sides? Yeah, because that way I get rid of the x on the... I moved stuff over to the right-hand side, and then I wrote it on the left-hand side. To confuse the students, of course. You know, it's one of my goals. Not really. And then I think that factors, right? So it's minus 4 times x minus 1, right? And so the solution would appear to be x equals to 1, x equals to 4. But here's the thing. Whenever you square an equation, it's possible that you've added new solutions that weren't actually in the original solution set. So you have to go back to the start and check if these are actually legitimate solutions or if they're extraneous, right? So how do we do that? Well, how about this one? So check it out. It's square root of 5 minus 1 plus 1, which is what? Square root of 4 plus 1, which is 2 plus 1, which is 3. Is that equal to, question mark, 1 minus 2? So I'm plugging x equals to 1 back into the original equation, and what I'm finding is 3 is equal to minus 1, which is not true, right? So this is an extraneous solution. It's not even in the solution set. Now, x equals to 4 is so x equals to 4 works. When we plug it back in, it actually does solve the original equation. Why don't we have to go back and check the solution for like these kind of problems? Why is it just these ones we have to go back and check? Yeah, those we're not solving. The thing is, we never did anything here that like changed the solution set, right? We're just using the logic that when the product of the factors is equal to 0, it must be that at least one of the factors was 0, and that allows us to logically list the answers as, you know, plus or minus 12, plus or minus 1, or the other one as 0. Over here, when we square that equation, we have added new solutions. See, the thing is, if you think about it, what if instead of this problem, we had been given minus the square root of 5 minus x equals to x minus 3? If we had been given that equation and we squared that equation, we would have gotten the same stuff afterwards, right? So when you solve these, you have to be careful. You've added in solutions that are not actually solutions to your equation. That doesn't happen every time, but it happens sometimes. So, yeah, go for it.
For problem 1,
Mission 1, yeah.
what is the upside down?
Oh, very good question. So upside down U. So let me just take a step back from these fancy intervals and such, and just look at a set with like a couple of elements, real basic, all right? So like we could have a set A containing, say, the numbers 1, 2, and 3, and our set B could be the number 1 and a cat, all right? And then you could look at the union and the intersection of these sets. So like A union B, logically what that is it's X such that X is an element of A or X is an element of B. And you guys, like the other section, at least half of you don't know what I mean when I write the funny looking E, right? So what this is, oh, come on, element of. You're like, oh, I don't know what that means. I know that. That's why I'm talking about it. If I just told you things that you already knew, there would hardly be a point in being here, would there? Right? So element of. So either X is an element of A. I shouldn't say either. X is an element of A or X is an element of B. It could be that it's in both. All right? This is like the mathematical or, not the exclusive or. So what is that? We got 1, we got 2, we got 3, and we got a cat. That's the union. What's the intersection of A and B? So this is so-called union. U for union, if you like. N, not really. I mean, it kind of looks like an N. It's not an N, though. It's just the upside-down union. It's like a horseshoe, if you like. But this is for intersection. Logically speaking, the definition of intersection is X such that X is an element of A and X is an element of B. So in my silly example, what element is common to both sets? Yeah, just the number 1. So the intersection here is just 1. Since you asked, and it doesn't hurt to spend a minute, another thing you could do is you could draw some pictures of sets, and you could visualize union and intersection using what are called Venn diagrams. So this is A. This is A. This marker is near death. Oh, man. Oh, there it is. Deep purple. Here's B. Right? So A union B, what's that look like? So it's just like everything, right? You just put both together. That's the union. The intersection, if you want to visualize it, it's just this piece right in here. So we need the union to describe the solution set to certain inequalities. Because sometimes we have like an interval, we have another interval, but they're not next to each other, so we have to take the union of them to get that kind of set of real numbers. Let me look at a problem which works out like that. So here's an inequality problem that'll be like that. So here's just a quick reminder. It may not be a reminder. Maybe the first time anybody's telling you it. I'm not sure, you know. But here it is. If you wanted to solve the absolute value of A less than or equal to C, so here I'm assuming C is positive, okay? Then that is interchangeable with minus C less than or equal to A less than or equal to C. On the other hand, if you have the absolute value of A greater than or equal to C, that is interchangeable with, let's see here, A less than or equal to minus C, or A greater than or equal to positive C. I mean, I can explain why this is to you if you'd like. Sure. Okay, so let me do it with an example rather than this kind of abstract A and C. So suppose we have like 3x plus 8 absolute value greater than, I don't know, 11. What does that mean? There are two possibilities, right? The possibilities are either 3x plus 8 is greater than 11, or what? Minus parentheses 3x plus 8 is greater than 11. See, because the absolute value of 3x plus 8, it's either plus or minus what's inside the absolute value. That's how absolute value is defined, right? So we have two inequalities to solve. And this one, we've got 3x greater than 3, right? Because subtract 8 from both sides, 11 minus 8 is 3, right? On the other side, we've got minus 3x is greater than, I have to add 8 both sides, right? So one more step in here. This is minus 3x minus 8 greater than 11, right? Which is giving us minus 3x is greater than 19. So over here, one more step, we're done, right? X greater than what? X is greater than 1. How about the other side? What's this? We clean that up, what do we got? Yeah, X is less than minus 19 over 3. You're like, what, but it was greater than. Why is it less than? Because I just, yeah, divide by a negative number, right, yeah. Now, okay, so we can draw a number line, right? And I'll use red for this one. 1 is here, let's say. So this is this x, right? That x is somewhere to the right of 1. Its x is larger than 1, greater than 1, right? On the other side, we have what? X is less than minus 19 over 3, which is, 6.333 or whatever. But the point is, this is over here somewhere, right? Notice that this x and that x are logically not the same value, right? We're using the same letter x to denote two separate values. These cannot be the same value. You cannot satisfy both of those inequalities at the same time, right? So, what does that mean? That means that the solution here comes in two pieces. And that's why we need union. So like this piece is minus infinity to minus 19 over 3. This piece is 1 to infinity. And we can put them together with the union. And so an interval notation solution is minus infinity to minus 19 over 3, unioned with 1 to infinity. So there's the, like in the mission 2, when you guys get a chance to look at it, you'll see I've asked you to write the answer to certain inequalities using interval notation, and then I say you might need to use a union. This is what I'm talking about. Yeah. Set builder notation is like this. This is set builder notation is like when you write the curly brackets, the thing that you're interested in, and then conditions on that thing. So the set builder notation is like the curly bracket stuff. So like, for example, AB is the interval. The set builder notation for that would be like x such that A less than x less than B. So this guy is set builder notation. Set builder notation. The this, on the other hand, is the interval notation. interval notation is also dangerous as we start studying coordinate geometry, right? Because we also use like 1 comma 2 to denote the point in the Cartesian plane with x coordinate 1 and y coordinate 2, right? So there is this ambiguity with our notation. It doesn't usually hurt us, but it's something to be aware of. We have overloaded that notation, so to speak. Okay, let me move on. So I need to talk about, how to solve more interesting inequalities. If the inequality involves an absolute value, we can break it up into two, and we can do it like this, right? And that's fine. But let's see here. How would you solve more interesting inequalities is a question that I should answer. I think that I'm burying the lead here. So I'm a little bit behind in terms of the material we're covering. I want to make sure we have enough time to properly discuss inequalities and everything, and just answer questions about the mission next Tuesday. Next Tuesday you'll be asking questions about mission 2, because at the start of class Tuesday you have to turn in mission 1, right? So there's no questions about mission 1 on Tuesday. Like today was the last day for that. Of course, I do have office hours, from 10 till noon, and you're welcome to come ask questions then. You can send me emails. I'll try to help you. Like, I'm here to help, but I do need to collect mission 1 at the start of class Tuesday. But once that's done, I can answer questions about mission 2, right? Of course, I also have material we need to cover, but getting to my point, I'm omitting sections 1.7 and also 1.12. These are both word problems, and I just think we have enough math to do right now that we don't need word problems to like come in and add confusion. So I'd like for you guys to be able to focus on, making sure that these basic math steps are really, really well polished before we start doing word problems. We can do word problems later in the course if they come back to it. And most of you are going to take calculus anyway, right? You say no. Yeah, the other section was perfect. They were very like, oh, that's for the best. It's fine. I usually don't have objections when I remove word problems from a course. But the other reason is I think word problems are more fun in calculus when you have the proper technology to do word problems, because I think word problems just get that much more interesting in the context of calculus. Okay. So I have at least covered sample examples of like solving the different kinds of equations that we throw at you, right? And I think you probably, if I erased these absolute values, right, and just said solve this linear inequality, I think you guys know what to do, right? Then you just have one inequality solve, right? But there are harder things that we need to talk about. Like, how do you solve an inequality? Start out with this example. X squared plus, let's say, 3x plus 2 greater than 0. How do we solve this kind of inequality? Factor it out first. I like that. So how do you solve this kind of inequality? Mm-hmm. See, that's the thing, is before when we were doing equality, whenever we got to the step AB equals to 0, we knew what to do, right? Either A equals to 0, or B equals to 0, or both. So we can divide and conquer like that, right? But what about here? When you have a product of two numbers is positive, what does that mean? Yeah, it could be that A and B are both greater than 0, but what else could it be? They could both be less than 0. So you could either have plus plus or you could have minus minus. Either way, your net is positive. So we have to break up into two cases. So case 1, x plus 1 greater than 0, and x plus 2 greater than 0, right? And that gives us what? X greater than minus 1 and x greater than minus 2. Can we do that? Can we have x greater than minus 1 and x greater than minus 2? So which one do we keep? We have to have both for it to work, right? So when you're thinking about and, you want to look at the intersection of the sets which are underlying the question. Like, this is minus infinity to infinity. If we want to look at that solution in like interval notation, this is minus 2 to infinity. If you intersect these, negative 1, right? So what I'm trying to say is there's some thinking involved, right? How about case 2? We would need x plus 1 less than 0 and x plus 2 less than 0, right? Which would mean that we would need x less than minus 1 and x less than minus 2, right? So just to, if you want, you're like, well, you thought through that other one. Another way I could like maybe convince you more is that minus 1 is greater than minus 2, right? That's why that did both of them. That's why we got both of these conditions at once by choosing that one. Over here, if I want x is less than minus 2, right? Minus 2 is less than minus 1, right? So I would choose the x less than minus 2 there to get both of those conditions to work. So in other words, for the first one, I have minus 1 to infinity. And for the second case, I get a solution of minus infinity to minus 2. So in total, solution is minus infinity to minus 2 unioned with minus 1 to infinity. You could draw that on the number line, right? So you've got like minus 2 to infinity like that, and you've got minus 1 to infinity like that. That's the solution. It looks like that. Is this surprising? I mean, it really shouldn't be surprising if we graph the polynomial. Let me just introduce that. So how would we graph y equals x squared plus 3x plus 2 here? What are the x-intercepts? Minus 1, minus 2. Yeah, it's opposite the sign that appears in the factoring. I know. It's easy to turn around on that. Have I done it wrong? Oh, I did it wrong yesterday, so I'm legit asking you if I did it wrong. I will flip a sign in my head from time to time. So those are the x-intercepts. This is a parabola which opens up. In fact, it's got a y-intercept of what? 2? right? Because of this 2 here. Plug in x equal to 0, we get y-intercept of 2. So basically, this guy looks something like, it's a bad picture, but that's roughly it. So you're asking the question, the original question is, right, for which x is x squared plus 3x greater than 0? That is equivalent to the graphical question, where is the graph of that quadratic above the x-axis? Is it surprising that we have 2 disconnected intervals for the answer? It's not at all, right? Because if you look at it, you can see the solution that we found, right? It's this piece, and it's that piece, right? That's where it's positive, there and there. And that's why this math worked out like this. Now, you should be happy when I tell you this is not how I'd like you to show your work. I think that, I mean, this is logical, it's methodical, it's not a bad way, but there is a much faster way to solve these kind of inequalities where I think you'll have much greater success. And that other method is really based on the idea that if we look at the graph of a polynomial, right, or the graph of a rational function, something like this, the only way it can change from positive to negative is what? Where do polynomials or what's a rational function, by the way? You're like, we haven't talked about functions yet, so I don't know what you're talking about, sir. Fair enough. So the next chapter is functions, right after test 1. But hopefully you have talked about graphs of rational expressions in intermediate algebra, like still a little bit. Maybe not. I don't remember. After all, it's hard for me to remember a course I haven't taught yet. My apologies. But I'll just show you another example. If we looked at like y equals to, say, 1 over x plus, I don't know, 1 over x minus 1, something like that, then the graph of that, it's got like these, let's see here. So if I put in, let me try plugging in a value. If I plug in like minus 1, that's negative. This is also negative, so it's negative over here. So once I get started, I'll be able to finish it. But this basically looks like this. There's this vertical asymptote right there. There's another vertical asymptote at 1. So x equals to 1 and x equals to 0. These are so-called vertical asymptotes. By the way, I don't believe this is on your first test. I'm actually kind of telling you things we're going to do later in the course. Actually, this is much later in the course, but it's helpful to have this little talk right now to understand what I'm about to show you. And anyway, so I believe what happens is it does some kind of deal like this, and then it's like this over here again. So here, this is a plot. The graph looks like these red lines, right? So where would this happen? You could figure out where that is by setting that plus that equal to 0. That would help you figure out where the x-intercept is. You're not responsible for this right now. This is like later, this particular thing, I believe. And so that's a good question. What are you responsible for? Primarily complete missions 1 and 2 with understanding. If you can do that, you should be ready for the test. All right? Anyway, my point to you here is that we changed from positive to negative either at a place where it's 0 or a place where there's a vertical asymptote. Now, for me to get the 0, I have to do some algebra to see it. Make a common denominator here. So, in fact, when is that 0? My picture's not very good. The 0 is at a half. So, like, if I drew this picture better, I should have known. The 0 actually is right here. If I drew my picture better. So, now that I've done all this work presenting this graph for you, we could do what? We could solve like an inequality, right? So 2x minus 1 over x times x minus 1 greater than 0. Can you solve? I mean, you could easily solve that since we have the graph right there, right? This is positive wherever the graph is above the x-axis. So like, I saw someone shaking their head no, but it's like this piece right here. This is above the x-axis, right? So that's going to be, those x are solutions. These x over here are solutions. So from this graph, I can tell you the solution is 0 to 1/2, and not included, unioned with 1 to infinity. So you're like, this is not helping because I don't want to graph these things, right? Does the shape of the graph actually matter to these arguments? It doesn't, right? What really matters is just the plus or minus, right? The sign of the expression. We can gather all that information just with a simple number line, okay? So let me show you exactly what I mean. I'm going to redo this example using the number line technique, and then I think you'll feel better. I'll stop trying to explain and just show you how to do. So to solve x squared plus 3x plus 2 greater than 0, we do just like we did before. We factor. And then just draw a number line. And on that number line, right, what we're going to do is we're going to mark down any interesting numbers for the expression. What are interesting numbers? They're either places where that expression is 0 or where the expression's undefined. So like for this one, the places it's undefined would be 0 and 1. It's 0 only at 1/2. There'd be 3 interesting numbers for this one. This one, on the other hand, is there any place where this polynomial is not defined? If I asked you to find the domain for this expression, what would the answer be? Negative infinity to positive infinity, right? The whole real line. There's no terms and conditions here, right? Like, the domain is genuinely unlimited. It's not like just plus or minus 30 because of the, the volume of calls at a certain time of day, and you have to limit data hogs because, sorry, I'm still bitter about my unlimited plan, which was not unlimited. But anyway, so here, interesting numbers, -1 and -2, right? Don't be like me. Sometimes I'll put -1 first and then put -2 second, not thinking about it. That will make your answers wrong. So make sure you put the more negative number to the left. That's how number lines work, right? And now what do? Now I just choose a test point in each subinterval. So you just got to tell me one number to pick in. We pick any number, plug it in, -3. Very good. So I'll do the work down here, like -3 plus 1 times -3 plus 2 is what? -2 times -1, right? Which is 2, which is positive, right? So that tells me I've got pluses over here, plus, 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 plus. Right? Now I need to give me any point between -2 and -1 at a test point. -2.5, your heart is in the right place. I never tell students their heart is in the wrong place. Yeah, -1.5, yeah. Pesky negative numbers. So like put a -1.5 in. So -1.5 plus 1 Minus 1.5 plus 2, what do we get? We get minus 0.5 times 0.5, which is minus 0.25. The point is it's less than 0, right? So that makes me put minuses there. Now I need a third test point because I've got a third interval to look at, right? To the right of minus 1. 0. I like the way you guys think. 0 is the laziest choice, therefore it is the right choice. So 0 just gives us, well, plug in 0, we get what? We get 2, right? Do I need to write anything down for that? I don't think I do. In fact, usually, guys, this stuff I'm writing down here, this is optional. It's totally reasonable to think about plugging the numbers in your head and just putting pluses and minuses here appropriately, right? So I'm putting this, I wrote this out here so you'd understand what I'm doing, but when push comes to shove, it's fine to just put the pluses and minuses up here. Just be careful when you plug in the point, all right? But yeah, there's plus over here because plug in 0, we get 2. So all we have to do to solve inequalities involving this quadratic is to look at the number line and just reason. What's the answer? If I want to solve greater than 0, that's where the pluses are, right? So that's why this was the answer. I don't have to go through this tedious consideration of two linear inequalities joined together and pick which one dominates and all that. I can just draw a number line and write the solution down. Yep.
Why did you put the imaginary?
This one? It's because that's negative, but 2 minus 1.5 is positive. So it goes minus plus, which is why I get a minus.
How many greater than? Why did you put it?
Because 2 is greater than 0, but minus 0.25 is less than 0. Yeah. It's because the numbers were different. So, again, from this, I can tell you, from that, I can immediately tell you that minus infinity to minus 2 union with minus 1 to infinity solves x squared plus 3x plus 2 greater than 0. But you see, could you tell me what the solution is if I say less than or equal to 0? What's the solution if I, instead of asking, what if I ask the related but slightly different question? X squared plus 3x plus 2 less than or equal to 0. If I've already done this work, I can immediately solve that. Just looking at the number line. What's the solution? Yeah, minus 2 less than or equal to x less than or equal to minus 1, right? I'm trying to write answers in interval notation. So what's this in interval notation? It's just minus 2 to minus 1, close brackets. There you go. That's the solution. Once you understand this, we can solve much more complicated inequalities by the same method. It's really not much more work. By the way, what would happen if instead of like x squared plus 3x plus 2, you've got 1 over 3x squared, x squared plus 3x plus 2. What if we took like the reciprocal of this? We'd still get the same number line. It's just that instead of having zeros at minus 1 and minus 2, we'd have places where the expression's not defined. But the general rule of thumb is the expression can only change from positive to negative either at a point where the expression's not defined, at a point outside its domain, or at a place where the expression's 0. Now, so one more example, and then I'm going to go on here. So if I had, let's say, x plus 2 quantity squared times x squared minus 1, and I wanted to solve that greater than 0, how would I do it? So the first order of business with this one is to convert it into, I need to do a little bit of work here. See, this is x plus 2 quantity squared. Can you guys factor x squared minus 1? Yeah. X plus 1 times x minus 1. Right. Now it's completely factored, so I kind of take ownership of it, you know? Yep.
Why don't you go ahead and square it first?
It doesn't, I mean, it's already factored. I could square it, but it wouldn't help me. Okay, so what's the number line look like? I mean, you could do that. I just don't know. I don't think it would accomplish anything you're interested in, you know? What are the interesting numbers here? Where can it change sign? It can change sign at minus 2, and also at minus 1, and also at 1 again. Right? So I put those down. Minus 2, minus 1, 1 again. X plus 2 is 0 when x is equal to minus 2. So remember, if we have a factor of like, whatever appears in the factorization is like the minus of that, that's the root. It's the root, that's the 0 we're looking for here. It's because, you know, x plus 2 is equal to 0 when x is equal to minus 2. And now we got to plug in some test points, right? Let's see here. So I will, I'll be lazy and start at 0. What happens when you put in 0? This gives us 4. This gives us minus 1. Gives us it works out to minus 4. Basically at 0, this is positive, this is negative. Plus times minus is minus, right? So here we've got a negative. What happens when you plug in 2? If I plug in 2, 2 plus 2 is 4, right? So yeah, that's positive, that's positive, that's positive. We got positive, 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 we got pluses. What happens when we plug in like minus 1.5 as a test point? So minus 1.5, that's positive, right? That's negative. That's also negative. So we get plus times minus, that's a net plus. And then if we go to the right of minus 2, what we're going to have is a plus times a minus times a minus. It's again going to be plus. So that's something you can look for. When you have a factor which is